I'm Ennemcien. First of all, thank you, Western, for your response. Problem. A bent wire of mass m and length L is immersed with its two ends in mercury. The wire is in a uniform magnetic field B. When a charge Q is passed through the wire, it jumps up to a height h. Find the value of Q. This is the arrangement. These are two mercury poles. This is the wire of length L. There is a magnetic field directed into the plane of the paper that is perpendicular to the conducting wire. A charge Q is passed through. A current is passed through this wire by means of a cell, an electric cell. Then it jumps up. You can check the direction of this motor force using LMP rule. It will move up to a height, say in the question it is given to be h. Then what is the charge passing through this wire? That is the question. Now velocity with which it jumps, we can find it out as a root of 2gh. When you throw a body up, you can solve using the equation v square equals u square plus 2as. Here u is unknown, v is 0 at the height s equals h, a equals minus g. Then will you get u as the square root of 2gh. Then the lower motor force on the wire is given by F equals B-bil, B-I-L. Therefore, impulse of this force for a time t equals change in momentum, impulse momentum principle. That is, impulse F into t equals mu minus mv. The change in momentum, either initial momentum minus final momentum or final momentum minus initial momentum. Only change in momentum is required. Here mv is 0. mu is m into root of 2gh minus 0. F is bil into t. But we know that I equals q by t. So that I into t equals q. So you can put I into t as q. Then the equation becomes BLQ equals m into square root of 2gh, from which q equals m into root of 2gh by BL. This is the answer. Another question. This is an AC circuit, LR circuit. Applied voltage RMS value is 10 volts. Frequency is 50 cycles per second or 50 hertz. R value is unknown. Inductance of this coil is 0.01 Henry. Voltage of this coil is 6 volts. Here the first question is find VR, voltage across resistance. B, current in the circuit. 3, value of R. for impedance of this circuit. Remember that voltage, summation of voltage in AC circuits is quite different from that in DC. In DC, you can just add the component voltages to get the total voltage. But in AC, you have to rule parallelogram law. Here, VR, VL. This is V. Then V square equals VR square plus VL square. I have taken it in earlier class. So that VR equals square root of V square minus VL square. That is square root of 10 square minus 6 square, or 8 volts. That is the first answer to the first question. Voltage across the resistance is 8 volts. Not 10 minus 6, 4. It is 8 volts. 8 square plus 6 square equals 10 square. Pythagoras theorem. Then, second question. We know that VL equals I into XL. That is I into omega L. Therefore, I equals VL by omega L. VL is voltage across the coil. That is, I equals VL is 6 volt. That is given in the question. So, 6 by omega is 2 pi F. So, 2 pi into 50 into L value. Self-inductance is 0.01 Henry. The answer is 6 by pi ampere. That is the second answer. Then, third question. Resistance, value of the resistance. R equals voltage across resistance by I, or VR equals I into R, or R equals VR by I. That is we have VR, that is 8 volts. So 8 by I is 6 by pi. That is 4 pi by 3 ohm. That is value of R. Then last question is total impedance of the circuit. You can find out it either using the formula, direct formula for Z. Z equals square root of R square plus omega square L square. That will involve tedious calculations. You can simply use this formula instead. V equals I into Z. Total applied voltage equals current into total impedance. So from which Z equals V by I. That is 10 by I is 6 by pi. Answer is 5 by 3 pi ohm. That is the total impedance. Subscribe the channel and see the earlier postings for better understanding of the subject. Thank you. Another question. Current through a 0.1 millihenry induction coil. I'm sorry, I shall read once again. Current through a 0.1 millihenry induction coil is increased from 2 ampere to 6 ampere. Find the work done by the source of current. We know that energy of a solenoid through which current I ampere is flowing is given by half Li square. Here let I1 be the initial current and I2 be the final current. Then initial energy is half L I1 square. Final energy is half L I2 square. So change in energy is half L into I2 square minus I1 square. This must be equal to the work. Work is converted into energy. So work done by the source of current is W equals half L into I2 square minus I1 square. That is half into L is 0.1 millihenry, that means 0.1 into 10 raised to minus 3 into I2 is 6 ampere, 6 square, minus I1 is 4 ampere, 4 square. The final answer will be 16 into 10 raised to minus 4 joule. Simple problem. Another one. A magnetic field produces acceleration in a charged particle because of Lorentz force. Does the field alter or change kinetic energy of the particle? Explain your answer. When a charge enters a magnetic field, it experiences Lorentz force. Lorentz magnetic force is given by Q into V cross B. This force is perpendicular to both B and V, velocity of the charged particle. Whenever force is perpendicular to velocity or direction of motion, work is always zero, because work in the formula a cos theta comes. Theta is the angle between force and displacement or velocity. That means work done by magnetic field is zero. Since there is no work done on the charged particle, kinetic energy of the particle won't increase, will not increase. Or a magnetic field cannot supply kinetic energy to a charged particle. That's the answer.